Okay, let's get started. So here's our exam one review. And we're going to be going up through including transformer tests and per unit. So, excuse me, it's hopefully a lot of review for most of you. That's why there's a lot of varied topics. But excuse me, it's not anything particularly difficult, I think. It's just stuff that you may or may not have had experience or exposure to in quite a while. So in this class, we do everything from a steady state analysis perspective, meaning everything is going to be averaged values over one cycle. And when we do that, it massively simplifies our work because we no longer have to worry about looking at resistors, inductors, and capacitors and having to solve differential equations to solve for voltages and currents. What we can do instead is do the concept, the idea or the concept of steady state. And now everything is treated essentially as a resistor, meaning we use our V equals IR for Ohm's law, but instead of IR, we'll go I times Z, where Z is an impedance. And it can be a purely real impedance as a case of a purely resistive load, or it can be purely imaginary in the case of purely capacitive or inductive loads, or it can be a mix of both. And so you may or may not have a J term or a real term, just depending on how the circuit is configured. And again, the nice thing is we don't have to solve differential equations. That's the biggest reason why we do AC circuit analysis. And nobody in the power industry, if you're doing things from a longer term perspective, actually needs to do anything in the time domain. If you do stuff in the time domain, you're looking at stability analysis, or you're looking at wave propagation because of lightning strikes, that type of stuff. For most of us, we won't need to worry about that. So that's our term Z. And when we moved on to that, we still need to recognize that we have the J terms, because that term is indicating that it's not consuming any real power, but it's storing power. So it increases the magnitude of the current. And that's why we have to add the impedances there. But we're not going to add them as real terms. We're going to add them as imaginary. And we add the J for the inductive terms because we get a 90-degree phase shift, right? Remember Eli the ice. And we have a negative J, or 1 over J, for the capacitor because, again, the same concept, right? It's Eli the ice. And so we just need to think about what phase shift that we're getting. All right. And then we really needed all this stuff because we can extend that to the concept of power. Because again, a lot of engineering is about how to use power effectively to make our lives better. And we don't just have instantaneous power like most of you all are familiar with. We look at things over the average of one cycle, and we need to consider the fact that some of the power that was sent out in part of the cycle has to be returned back to the generator. And so how we quantify that is with a power triangle. And the power triangle is always a right triangle. It's always going to be in quadrant 1 or quadrant 4. When I talk about quadrants, right, that's the graphs here, where we're looking at quadrant 1 or quadrant 4, the regions in our XY Cartesian plot. And it's always going to be in 1 or 4 because our power is always positive. Whether it's a load or a source, power is really what's going to dictate the direction of the current. And that might be a little bit of a flip around because what you were probably taught is current dictates a lot of things. No, it's actually power. Is it a source? It is a load. Then power is either going in or coming out of the different types of pieces of equipment. So our real power always rolls along the x-axis. And our reactive power or imaginary power, and again, it's not imaginary, it's that borrowed power. So it's actual power that's doing something. That is going to be not actually being, it's not going to actually be used up in the system. So that is the one that's sent back. So we don't put that on the real axis. We put that on the x-axis. And then the vector addition of those two powers becomes our total or apparent power. And how do we get total or apparent power? It's S equals VI conjugate, okay? You've got to have the conjugate because if you remember when we did our trig identities, when we introduced the power triangle, we had S equals P times I, and it was the magnitude of V at an angle of theta V, times the magnitude of I, but we had to subtract the angle associated with I. So that's the only reason why you use the complex conjugate terms. And one of your classmates was in the class this morning, and how do you solve for the power factor? It's not anything that we developed in this class. It's because we have a right triangle, so we can use the trig identities to solve for whatever parameter we have. As long as we have two elements, we can solve for it. In most cases, you're going to have P and S, or you'll probably be given the power factor and P. So you should be able to calculate all those different parameters using SOHCAHTOA. Power factor, which is just the definition of ratio of real power to total power, that's just P over S, which happens to equal, because of SOHCAHTOA, the cosine of theta, the angle between the P and the S. And since S equals VI conjugate, which is the angle of V minus the angle of I, that is exactly the same angle as the impedance angle that whatever load is connected to this particular one. So if you can get a power triangle, you have to be able to get, or have to be able to recognize, that that angle theta is the same as the angle between P and S. All right, that's pretty important. We also talked about the concept of leading or lagging. So we started out with Eli the ice, and then I started teasing you or trying to push you what's happening Eli the ice. Remember, it's always what is current doing. Is current leading or is current lagging the voltage? Not what voltage is doing, or not what voltage or current doing. It's what current's doing. So in Eli, the current lags the voltage in an inductor. So in an inductive circuit, it is considered a lagging circuit. In ice, the current is leading the voltage, so that is a leading power factor. And the power factor only tells you the direction of Q. Q will be going in the same direction as P if it's a lagging power factor, but it goes in the opposite direction of P if it's a leading power factor, okay? So that means that I can be either absorbing or supplying Q depending on if it's a leading or a lagging power factor. Whereas power is always going to be in the direction of current, the Q can be in the opposite direction. No problem, all right? So don't get hung up on the fact that Q is going in a different direction. That's perfectly fine in real world systems. So our term Z, to expand on that a little more, we do everything in terms of impedance. And impedance is the actual circuit limiting, if you will, parts that will limit the current. And impedance has real parts and reactive parts, or real parts plus the J term times the reactive parts. And how do you get XL and XC? That was just taking the derivative. If you remember, L dIdt or C dV/dt introduces the 2 pi f either in the numerator or in the denominator. That's just because we have to take the derivatives or integral if necessary. One other thing that's talked about here is we can use P equals I squared R, or V squared over R, and Q equals V squared over X, or I squared times X. But, and I want to highlight this here because most of you all will forget, these are magnitudes. P and Q are scalar quantities. P is 1,000 megawatts. Q is 500 kvar. It's not J 500 kvar, it's 500 kvar. It's only when we add it in to get the total or the apparent power is that when we add the J term. But when you solve for P or Q, they're just scalar numbers. So you should never turn in homework or an exam that says Q equals 372.5 at an angle of 26, because it's a scalar quantity, right? And if you do that, it's because you did not take the magnitude of the voltage or the current. And the only reason why it's the magnitude, because remember, S equals VI conjugate, and the real part of S equals the power, right? So V times I conjugate is I over Z with a negative angle over here. And what ends up happening is V at theta V times V at minus theta V just equals V squared, right? When you take the conjugate and you multiply those two together, the theta V's will cancel out. So that's the reason why you've got to make sure you don't have any angles when you do the V squared or the I squared, okay? So highlight that, put that in your notes, make sure it's V squared or I squared. Then we did three-phase circuits. And again, this is a really, really, really important table. If you didn't realize how important it was at the beginning when we introduced it, I hope you realized it as of Tuesday when we started looking at the power transformers, when we had to move on both sides of the transformer, right? We did a test at 115 kV and another test at 34.5, and we had to jump back and forth. But more importantly, we had to figure out, when do I divide the voltage by a square root of 3? And when do I divide the current by the square root of 3? So if you don't have that in your brain and you can't draw that circuit out, using this table is going to be very helpful, because it tells you, is my phase voltage or my line voltage needing to be multiplied or divided by the square root of 3 to get the parameters? Because every single inductor, resistor, or capacitor is a single phase element. So it has to be the phase voltage divided by the phase current to get the actual value. Do not use line quantities. Or if you do use line quantities, you better make sure you know when to multiply or divide by the square root of 3. I just recommend draw a picture and use phase quantities, just like what we did on Tuesday when we did the transformer equivalent circuit. So in a Y, the voltages are off by the square root of 3, but the currents are the same. In a delta, it's the exact opposite, just like we saw on Tuesday. We also have phase shifting for voltages and currents, depending again on, if it's ABC or ACB sequence, and when you're going to line or phase voltages. So using that bottom table, we'll hopefully be able to understand, do I add the square root of 3 or not? If you get confused, you can always draw a Y-connected circuit. I'll call that ABC rotation. And if I want to solve for VA to B, that is VA minus VB, right? Does everybody remember that in their circuits class? When I say VA to B, that's VA minus VB, right? Not right. But I'm asking the general class. You all remember that? You understand when you're measuring a voltage, it's called a potential difference. So you have a red lead and a black lead. The red is on the positive and the black is on the negative. So it is subtracting the 2 points to actually calculate a voltage. So when you go VA to B, red is on terminal A, black is on terminal B, and it's looking at a difference. So if you wanted to write that, that's VA minus VB. Everybody here is pretty good at vector math. So if I want to solve for VA minus VB, I'll just take the negative of VB and add them together, right? And you can see you got a 30 degrees there plus a square root of 3 there, right? When you do the subtraction, when you're looking at a Y circuit. So if you get stuck, just draw a picture. I can see I've got 30 degrees there by drawing it, right? Everybody here, when I just did the negative VB, that wasn't a trick, right? Everybody's seen that from previous math or whatever. When you're subtracting a vector, you just phase shift it by 180 degrees, and then you tag it on to the tip of the other vector, and then you just add it. Okay? We always want to analyze circuits single phase because the other 2 phases are the same, and it can be very cumbersome to analyze 3-phase circuits and go from there. The only thing you need to multiply or divide by square root of 3 are your phasors. So to go from phase voltage to line voltage, or phase current to line current, you're either going to be multiplying or dividing by the square root of 3. Everything else is multiply or divide by 3. Even power. And you can say, hey, wait a minute, Paul, you're lying to me because there's a square root of 3 in that equation, right? But that equation only exists for convenience. The actual base equation is here. But we know V line or I line are going to be off by the square root of 3. So one of these is going to be divided by the square root of 3, right? To go to V phase. And as a result, I get the square root of 3 there. So the actual base equation to go from single phase power to three phase power is to multiply by 3, not square root of 3. So square root of 3 is only for multiplying or dividing for phasors. You only have two phasors, voltage and current. A phasor is a rotating sine wave. Voltage and current are the only two that rotate. Nobody else rotates. Your impedances are fixed and your power triangles are fixed, right? Because those are average values, so they're not varying with time. Okay. Calculation of power. Once you have a system, and it can be an incredibly complicated system, the way to solve this system is all you need to do is just calculate the individual P's and Q's for the system and then add them up algebraically. All the P's will be added together, all the Q's will be added together, and that's how you get your total load on your system. Don't try to calculate I's like doing a KCL equation, because you can get yourself in a lot of trouble if you're not being careful. Just add all the P's and the Q's together, and then it works really, really well. Power factor correction. We did power factor correction. If you all remember from power factor correction, the reason why we need to do that is because we increase the Q on the line, we increase the magnitude of the current that is required to deliver that Q, which means we have line losses in our system that aren't paying us any money. The utility has to pay for higher I squared R losses to deliver Q to a customer who isn't really using that, isn't being charged for that Q. So you as the end user will have to pay a penalty unless you improve your power factor to a level that is satisfactory to the utility. So if your original system is Q1 as shown here, and you're going to be paying a lot of dollars per kVAR, now what you need to do is take it to an acceptable level. So all you need to do is find a capacitor right there that takes your Q from this value and brings it down. So the Q of the cap literally is just Q1 minus Q2, or Q actual minus Q desired, right? Whatever the utility is telling you have to do. So if you want to solve for that value of Q, you draw your original power triangle, then you draw your revised power triangle, and you'll notice the power doesn't change because you're not adding in another generator. You're just adding a capacitor, which doesn't have any real power capability. So your P always stays the same, but your Q goes down, which means your magnitude of S drops and your I squared R losses drop down a little bit. So I showed this on one triangle, but because you could do this with multiple colors, if you don't want to have pens of different colors doing this, you can just show two adjacent triangles. So this is one triangle. This is original, and this is desired, and this is P, and this is P. This is Q old. This is Q new. And the difference between these two is Q cap. And the reason why this works is when you draw a power triangle that typically has a lagging power factor, the lagging power factor is going to be an inductive type circuit, right? Eli says it's a lagging power factor. So if we want to improve the power factor, we have to add some leading capability in there, which is what the capacitor does for us, right? It is a leading power factor, so it's going to give us a little more. And there's essentially no charge to improve the power factor. I mean, obviously, we have to pay and purchase a system that has capacitors and install it out there. But once it's there, it doesn't consume any real power effectively. So we can put a capacitor on there for almost next to nothing, and we can save ourselves quite a bit of money on the machine. Once you know what Q cap needs to be, if you want to actually size the capacitor, so let's say you you work for a manufacturer and you're going to sell a 10 megavar cap bank, you can actually solve for the actual size of the capacitor that you need in farads based on how big of a capacitor in terms of kVAR do I need. So if it's 10 kVAR, I've got that, which will allow me to solve for X sub C. Once I have X sub C, then I can solve for C. So if I'm asking you to solve for a capacitor on the exam, in farads, you have to go through that whole step. The only thing I haven't given you in any of this stuff, because I'll tell you what the power factor needs to be improved to, I haven't given you F, but do I need to? Why not? We live in 60 hertz, right? So that's one of those absolutes that you are in North America, you will be using a 60 hertz system. So if you see frequency, unless I tell you you're in England or you're in Denmark or wherever, then you will be using 60 hertz. You don't even have to guess. You don't even have to state that as an assumption. You just say 60 hertz is your frequency. Then our first sort of new-ish topic is determination of Y-bus, which what we found in the lab and the homework isn't all that particularly complicated, is it? But it's an approach. And here is that approach kind of laid out for you. First off is however many buses is going to be the dimension of your Y bus. So if you got a 50 bus system, you got a 50 by 50 matrix. If you have 1,000,000 buses, it's 1,000,000 by 1,000,000. So that'll help you sort of preliminarily lay out what your Y bus looks like. Make sure you do this in advance. If you have any impedances that are in series, you've got to add them in series as impedances first, and then you invert and get admittances. All right? Super, super important, because we know with admittances, when we add admittances together, that's effectively like adding resistors that are in series, or in parallel, I should say. That's not what we have here. So make sure anything that's in series, you add them first. Unless there's a bus between them, then technically we don't consider that in series. There's a bus between them, so we would consider that as a separate condition. Once we've got all our elements that are in series taken care of, now we can invert and convert our impedances to admittances. If we have, we're ready to build our Y bus, the diagonals are called the self-admittances. So to solve for all your diagonals, you're just going to sum every admittance that touches that bus, including admittances that go to reference or ground. Okay? Every single reference that every single admittance that touches that bus gets added in the self-admittance. Then the admittances that go between buses, those are called transfer admittances, those are going to be put in your Y bus by subtracting the actual admittance and putting the negative of there in that bus. So your diagonals for a typical real world system are going to have negative J terms, and your off diagonals will typically be positive J terms. Once you have your diagonals and your upper triangular matrix, your lower triangular matrix is found because you have I was gonna say not a transpose, but the transpose are the same. So the matrix is exactly the same on the top or bottom. Okay. So it's no problem if you want to do your bottom triangular one, if you wanted to do it, but it's a symmetric matrix, so you don't necessarily need to do it. It's totally up to you. It doesn't bother me. You can just say y12 equals y21, or you can solve for y21 independently. It doesn't matter. You'll just see it's the same number. And then that gives you Y bus. Once you have Y bus to do anything with it, you can invert, you can do what you need to do. Just be careful when you multiply matrices together, you got to check for dimensions, right? Most of you all are pretty comfortable multiplying, dividing matrices. Well, you don't divide matrices, you multiply by an inverse, but you'd be surprised during an exam how many times people have come to me and said, why isn't my equation V equals I times Y working? And then you just point out the matrices, and somebody spent 20 minutes putting in their calculator, not getting the right answer. where you just had to check dimensions. So write down the dimensions on the top or the bottom and just check to see if they jive. It's a pretty quick and dirty result. We talked about the purpose of a transformer, and the transformer really all it does, at least for what we're trying to do for this particular class, is either step up or down voltages and currents. That's all we do for transformers. They provide other benefits for us, but in reality, that's what we need them to do. So if you have a transformer, you define a turns ratio as the primary voltage rating to the secondary voltage rating. You can also do the number of turns on the primary to the number of turns on the secondary, but nobody in industry does that. Maybe the manufacturers do, but all you care about, like in the case of our transformer test data sheet, you had a 115 kV on the high side and a 34.5 on the low side. So what was the turns ratio of that transformer? Two? Is the turns ratio is that correct? Okay. I'm not saying you're wrong. I'm just asking, is this the right one? Be careful, because for a 3-winding transformer, it's delta Y or Y delta like this, the actual turns ratio is from here to here, right? So it's 115 kV divided by the square root of 3 divided by 34.5, right? Because we have to convert that Y, which is the 115 is across two sets of a set of windings, right? Two windings. But to get it across one single winding, we have to divide that by the square root of 3. So the actual turns ratio is as shown. Okay. We would still say the transformer is a 115 to 34.5, and we could probably get most of our calculations correct. But if we're doing things from a single phase perspective, we have to be very careful. So that was at the end of our material on transformers. When we talked about phase shifting and we talked about that turns ratio A, we needed to divide by the square root of 3. So one thing about turns ratio, if you step the voltage up, you step the current down. Yes, sir.
So is it because the 115 is Y connected that we're dividing it by 3, or is it just general case that you'll always divide primary by?
No, it's because it's Y connected. Remember, 115 is across two legs.
So it's a 34.5 is Y connected, then we divide that by 3. So the 115.
If it is, are both of them Y connected, or is just, yes, then you would divide the 34.5. Yep. Correct. Wherever the Y is, you would divide it, but that's only if you're going Y to delta. If you're doing Y to Y, you have to divide both sides by the square root of 3, which means you don't have to divide anything, right? Because it'll just work out in the wash. But yeah, you only have to do it on the Y side for a Y to delta. Yes, sir.
How about this is the one?
Pardon?
This is the one.
You still have to do it on the Y side.
If delta is on this side, the Y is on the other side, the second level,
Doesn't matter.
you do it on the Y side.
I always do it on the Y side, because if I have a delta Y like this, right? Then it would be 34.5 divided by 115K over the square root of 3. Because the square root of 3 has nothing to do with the fact if it's delta or Y. It has to do with the fact that what is the voltage? When I tell you what the voltage is, I'm giving you the line voltage, which is not the actual voltage across the winding. It's the voltage across two terminals of the transformer. Okay. Questions on that? Okay. Then we did transformer equivalent circuit models. Did we beat this enough on Tuesday? Full transformer stuff, because we just did exactly the same thing in our transformer homework, except, with the volume turned way up, right? Because what I've been giving you in class is let's just do single phase, but now with 3-phase, now we got to be careful about delta Ys, don't we? So maybe parsing through the data sheet and finding the right data might have been a little bit challenging, But I think, but most people probably missed was, when do I divide by the square root of 3 and when do I multiply by the square root of 3? All right. So that's why that homework was a lot harder than probably you thought, because I even showed you the data to use, right? On pages 9 and 10. But I didn't tell you about using the square root of 3. I wanted to see if you actually would be able to pull the two together. Whenever you're dealing with three phase, you've got to convert it to single phase. So just make sure you do that. Yes, sir.
Could we do another like real world example with value from like a real transformer?
Sure. I think I have one more. If you want. Yep. Let's just get through this and then we can go ahead and we can put one up. I was really proud of myself when I came up with this table. You all probably won't be, but I actually put it all in a table and I broke it down so it's all in one table. I even tell you the parameters. And if you look at the MATLAB file that we did on Tuesday, it actually uses the same parameters, but instead of calling open circuit and short circuit, I did no load and load loss, right? Because that's what the data sheet actually gave us. So it's all the same thing. I even showed you how to get Y and Z and gave you the parameters. I didn't tell you about putting them on the same side of the transformer like we did on Tuesday, because that's up to you. So if the tests are done on different sides of the transformer, make sure you reflect the impedances up or down as we talked about. Okay. That's what we talked about in the last one. So take a look at this table. I think it does a pretty good job of having it all condensed, you know, what the steps would need to be. And then if there's one thing that you can really hammer down this past, few weeks, it's per unit. Because in industry, that's the kind of what we use extensively. Everything is going to be a ratio because we don't want to reflect impedances through transformers. We don't want to respect voltages and currents. We want to make it super easy. So if we do everything as a ratio, where we're walking through a transformer and we're moving up base quantities up or down through transformers, then we'll do everything, as a ratio. The only things you have to do, pick one S base because the transformer doesn't change the power. Pick a single V base at a location. Then, as necessary, you calculate Z base and I base. And what we saw in lab this week is you didn't have to calculate Z base everywhere. Remember, we only had two lines that gave you impedance values. So you only had to calculate Z base in those areas. If you have impedance data that's given to you in per unit, then you're going to use this conversion one here on the bottom, right? That's the one that I would just copy onto your note sheet to make sure you have it set up to convert from old base quantities to new. Super duper helpful. And if we do single phase or three phase, it doesn't matter. We just have to be careful that our S base is three phase S base for our three phase system, and our V base is a line to line voltage. And then our I base equation has to be modified with that square root of 3. That's the only difference. If you do those correctly, you can analyze any three-phase system in per unit with a single-phase system, and you're going to end up with the correct quantities. So by picking those right values, it just makes it so that we've converted all of our three-phase quantities to single-phase quantities kind of behind the scenes. And here are specifically what I'm going to be testing you on. Only 6 problems. And this should be available on Brightspace, is it not? It is on Brightspace? Everybody know where to find it? Should be pretty easy. I just have it set up by class. So the date of the class. So everything, including the video link, should be in the class folder. If people find that that's too difficult to find things, let me know. We can try to come up with something different. But I try to make it easy to find stuff because you can tabulate it to the syllabus and, hopefully it makes it easy to go through. All right, let's see if I have another real world example. Let's see what's in here. Oh, great. I do have one. Is this one satisfactory? The little itty bitty transformer, but it's 3 winding. You can see it's 3-phase, 60 hertz, base rated for 36 MVA. So I'm going to highlight that. And I have 3 windings. I have 22.8, 6.9, and 4160. It doesn't matter when I do a transformer equivalent circuit model. If I have a 3-winding transformer, I'm either going to go 22.8 to 6.9 or 22.8 to 4160, or I can do even 6.9 to 4160. It really just depends on what we're trying to do. You can get that. So I know that. This one's a little harder to figure out, but it's a delta on the high side, a Y on one of the windings, and a delta on the other winding. So the 22.8 is delta, Y, delta for the 3-winding transformer. All right, so first thing we see is the no load loss test. And I can see, if I look closely, the no load loss test is going to be equivalent to the open circuit test. So I don't actually have a perfect 100% voltage. So how about we just use the 99.321, right? Close enough to 100%. Not exact, but close enough. So I'll use the 99.32. And actually, this one is even corrected. So let's go over here and do this corrected one, which is right here. Okay. So that's our load loss, our no load loss test. So we can see that our voltage is going to be equal to, is it 22.6? 22.8. So we have V no load is equal to 22.8 kV. That's 100%. I no load is going to be equal to 0.593. And the last thing that I need is P here. And I think the PR, let's see, that's not the reference temperature. So we're going to use 15.041 kilowatts. And I have enough information to do my parameters so that I can get R sub C and X sub M. But remember what we said, this is on the delta winding. So I had darn well better divide that by the square root of 3 to convert that to, not the, sorry, wrong one. I have to divide this one by the square root of 3 to get the magnitude of the current. Now I need the angle of the current. So the angle of the current, this is 15.041. The magnitude here is square root of 3 times 22.8 K times 0.593. The angle here is the no load test. So my theta no load is going to be equal to 15.041 K divided by square root of 3 times 22.8 K times 0.593. And don't forget, I have to take the inverse cosine of that because that would be the cosine of the angle. So I need to take the inverse cosine of that to get theta no load. Once I have theta no load, I can solve for Y open circuit or Y no load as going to be equal to 0.593 divided by the square root of 3 at an angle of negative theta no load. By the way, this is a positive number over here, right? Why did I put a negative number here? When I do the inverse cosine of 15.04 divided by that S value, I'm going to get a positive number. Why did I make it a negative number?
Because,
Because Eli told me to, right? What kind of a power factor does a lagging circuit have? A lagging circuit, I just told you the answer. What kind of a power factor does an inductive circuit have? Lagging. So if this is at an angle of 0, right? Then I know my current has to be at a negative number because Eli told me so. And when I do that, I end up with 1 over R sub C plus 1 over J X sub M. So you divide those number out, you invert them independently, the real part and the imaginary part, and you got RC and XM. Okay? That's the no load test or open circuit test. It's the same term. Just the manufacturers call it differently.
Hey, Paul, I got a quick question.
Yes.
So for the hypotenuse of that power triangle that you made, is it supposed to be 0.593 divided by the square root of 3 instead of
No.
It's not?
Alan asked a really good question. Why didn't I put 0.593 divided by the square root of 3 there? Yeah, because the square root of 3 here means that these quantities have to be line quantities.
Okay.
Not
Thank you.
case quantities. If I put a 3 there, then yes, I would need to do that. But because I use the square root of 3, I can just use the original parameters provided.
Okay. Thank you. I think that's what messed me up on the homework.
Okay. Now, look at the load loss. So the load loss test, we're going to use the, let's see, H to X, 345 to 69. I can't tell. I'd have to check out the currents, but let's see. So, oh, here it is. We're going to use the base power here, right? So that 18 MVA, that's what our base power is. That's typically what we're going to be using. So this one right here is what we're going to use for the load loss. So we can see that we have rated current, measured voltage, corrected voltage, etc. So my I load loss is going to be equal to 461.8. My V load loss is going to be equal to, it says corrected voltage, 1745, which is a good thing, right? Because we're applying this at the 22.6 kV side, or 22.8, which I think this one over here also is done at the 22.8. So remember how we did some in class where sometimes you do them on the same side of the transformer? In this case, 22.8 kV is not that hard to get for a voltage source. So they decided, it appears, to put both of these on the high voltage testing on the high voltage winding. Okay, when you get to bigger power transformers with higher voltage ratings, you would switch. Yes, sir.
Why did you think?
Excellent question. Why did I pick 18 MVA? Anybody? Usually the base rating without any sorry, I'm still dealing with a cold. Without any cooling is typically what you will set your parameters for. So 18, and it's not obvious from here, but my best guess is that one of these ratings, most likely this one, can only handle up to 18 MVA. So you're just going off the lowest rating just to make sure that you're consistent amongst all your pieces of equipment. So normally it's base rating, just like we did the 60 MVA. That was a 2-winding transformer. In a 3-winding transformer, you would just use your most limiting one. Again, because the manufacturer is going to be a hell of a lot easier to put a short circuit on the 18 MVA winding because I get less, I don't have to put as much oomph into it than I would at the 36. All right, so I got my V line to line, which is 1745. This is, I believe, on the X winding. So you can see that is the Y winding over here. So, but it's still being applied onto the delta. I don't know why it says 345, unless this is a different transformer. I don't think it is. Still the same transformer, I believe. So anyway, so at this point, it's going to be on the delta. I got to divide that by the square root of 3, and I get an angle over here. How I get the angle is I take the power, which is corrected loss, which is 33,609 over here, square root of 3 times 1745 times 461.8. Not the 461.8 divided by the square root of 3 like Alan asked. It's the 461.8 because I'm dividing by the square root of 3. That's going to give me theta no load, which I can plug into there. And then Z, load loss, is going to be equal to V load loss at an angle of 0 divided by I load loss at an angle of negative theta load loss. And that's equal to RE plus JX. So again, it's the same thing over and over again. It's just that for the load loss test, we do everything in series because it's the value of Z, right? We're looking for those series impedances. Whereas when I do open and short circuit, or the open circuit test, I do it in terms of Y. You can certainly do what we did in class. We did V squared over P to get the value of R, but I find it's just as easy to do it this way.
So we already have an impedance percentage there in
Yep.
per unit. Can we use that to not have to do any of those other calculations and just get Z straight out of it?
Yeah, so if you were in the real world, hopefully somebody will tell you, yes, you have the percent Z, right? Where is the percent Z? Was it on the next page?
It's all the way on it's the middle column, 7 point something.
Yeah, so this one actually gives you percent Z, and it gave you X over R ratio. If you looked in the previous test report, there was no X over R ratio. And in my one of my previous assignments was to figure out the X and the R, and they didn't say it. It just gave us the percent Z. So I had to figure out what the actual equivalent circuit was to go ahead and tease out the X and the R values. So if you can, yeah, just use the transformer data sheet to get that. But sometimes you don't have enough information. Oftentimes, they won't tell you what the R value is for the RE. They may tell you the X over R. But you can see the one that we did for Pasadumkeag, there was no X over R. So that just shows you, that just gives you additional information. But somebody went through and calculated all these based on those tests. Okay. Yeah, somebody wrote 345. I don't think that that's right. I'm pretty sure. This is called, well, I don't want to get too much detail because I'll get myself in trouble, but this is operating at 22.8. So it's on the terminals of the generator. It's not connected to the 345 kV yard, but they do have bigger power transformers that are at the 345 values. I think if you look at the other data sheet, it might actually have that. I'm not sure. So this is a big transformer. See the size of this one? 210 MVA. That's the base rating. So this one is about 3.5 to 4 times the size of the transformer that you guys did your homework on. But this is a single phase transformer, which drives kind of crazy, right? But remember when we talked about really big transformers, they're hard to ship over the roads. So what they do is they just make 3 separate transformers and they connect them in delta Y as necessary at the field to make it work. So this is a single phase transformer. Just ignore all the information. Probably not supposed to get all that stuff in there, but you can get that. Noah. Work through the math? What do you mean? Like put it in MATLAB?
uh,
1745 times 461.8.
that seems like a crazy power factor.
Why? What's the power factor?
Will be 33,609 divided by that product, right?
Yep. Then take the inverse cosine of that.
Well, that would be.
Angle. So what's the angle? Yeah. This is a pretty high X over R ratio, right? 35. So that should be a pretty big number. Pardon?
Yeah.
Absolutely. Why would I want a very low power factor? Because if I built a transformer that had a high power factor, that means it's got a lot of I squared R losses in it. That means it's wasting energy, getting hot. That ain't a transformer I want. I want my R to be as low as reasonably practical so that I'm not paying for the I squared R losses in the transformer. That's where all the heat comes from. So I really want my X value to be much, much higher than my R just from an efficiency. There are some other challenges. So when I say X over R ratio, if you look at stability, there is something about looking at percent Z and X over R ratios, but that's way more advanced than what we would be doing here. So we won't get into that. But in some cases, the utility will tell you what your allowable range of impedance needs to be. So they typically tend to be fairly high for big power transformers like this. Anybody know what like a standard pad mount you walk around and what you would see would be an impedance for like the pad mount that's right outside the building? Usually it's 2.25. Pretty small. But power transformers, big power transformers, I don't think I've ever seen anything less than 7. Taylor, I think, has got a lot of experience. He may have seen something different, but I've seen him almost as high as 10. Well, actually, the one we did in this class was 9.4, right? At the base rating. So 7 to 10 is a lot more common for what I've seen. I don't know, Taylor, if you have any different experience, but a lot of this stuff is probably confidential information, like we're not supposed to share. Although percent Z, I don't think you'll get into too much trouble. Because I don't think the terrorists can use that information to blow up anything, knowing what the percent Z is, but you never know, so. All right, was that helpful to do that problem? The test will not have one that's difficult as a homework. Because I was asking you to do a lot. But I was also asking you to think, like to try to pull a lot of these things together.
What would be the range of the question now?
Here's some impedance data, here's some load loss and no load test data. Tell me the circuit.
They're pretty much the template and slide for
I wouldn't say pretty much. I mean, basically, why would I? It won't be exactly the same, but it'll be on the order of something like that.
same kind of data given.
Similar, yes. Other questions? This is your review session. You still have. Yes, sir.
So on your workspace announcement, you said you can use MATLAB or a calculator. Does that mean one or the other, or yeah, like both?
When I say or, what does that mean?
One or the other?
One or the other. We talked about that in class. And the reason why you can only use one or the other is if you've taken the time to learn how to be proficient at MATLAB, you're probably not going to be skimming through Google pages, but I will walk around the classroom. And if you people are toggling back and forth, like you should never have to toggle away from MATLAB, right? Because if you're going to write a script file, you can do an editor inside the MATLAB workspace. So you should be able to just leave it up and do it there. So if you're toggling around, that usually is a bad sign. So I'm going on faith that people who are doing with MATLAB are going to keep the MATLAB prompt up. And if I see tabbing and all that stuff, then I have to collect your test, and that's plagiarism, right? So don't do that because it screws it up for everybody else. Because anyways, I'd have to go back to calculators only. And I really feel like everybody learns a lot more if they can use MATLAB. That's why I spend so much time going through it. What else? Yes, sir.
when you were talking about Eli the ice cream, it was like the next page up like before.
Why did I have the negative angle with the current? Yeah.
Yeah. How did it- I think it's on- without- and they're mostly like all industrial, right?
I can tell you right here. This is the equivalent circuit of a transformer. What type of circuit would that be indicative of? Is it a resistive inductive circuit or resistive capacitive circuit?
More stuff.
It's resistive and inductive, right? There are no capacitors. So based on Eli the ice, this is an inductive and resistive circuit. So Eli would tell us that this is a lagging power factor. So you have to be able to look at this and say, I know it has to be a lagging power factor because I don't see any capacitors in here.
Yeah.
So my equivalent circuit tells me that it's lagging. Mason, did you have a question?
Yeah, mine's about the home.
Oh. Okay. Yes, sir.
So, in the tables that you have, when you have delta, you have the current being multiplied by square root of 3, but in the example that you just did, you divided the current for the no load and the load by some sort of thing. I was just wondering.
Anybody know why I'm dividing in the homework, whereas I'm multiplying here? Sort of. So I'm going to build you a transformer. And I'm going to have you test it. The transformer is a box with 3 leads. Inside, the transformer is configured Y or delta. So I don't have access to the inside. I only have access to line currents and line voltages. So I've got to go from line to phase quantities. So the reason why I'm dividing by the square root of 3 is because I've been giving you IL. Can you tell me what I phase is based on that equation? Should be able to, right? You just divide by the square root of 3. It's just algebra. I phase equals I line divided by the square root of 3. The only time you will ever see that you're given a delta with, and I've only ever seen one of these in my career. If you've got some test data and they're telling you these are phase currents, there's an actual CT in the delta. So there's a transformer, a current transformer physically inside the transformer tank, which is very rare. But like I said, I've only seen one of them in the thousands of transformers I've seen where you actually are measuring phase currents. So it's pretty safe to say that you're only going to be looking at line quantities. But there could be an oddball like that when I looked at it, it threw me for a loop because the drawing I had was so bad, I couldn't tell that it was a CT. They do happen, but they're pretty rare. Bear Swamp, that's how they configure it, which is a pump storage in another pump storage in Western Mass. They have CTs buried in the delta. What else? Nothing else on the test? Do you want me to end the set? Oh, go ahead.
I think that feel that in the 3-phase, so they calculate line and phase quantities. Could you give like an example?
Yeah, so if I have a delta here, the way the delta is connected is a tip to tail fashion. So remember, the phase quantity is always looking across a single phase. So this is a single phase power supply. I've got 3 of them in here. So the voltage here has got to be the same as the line voltage because the line voltage is measuring across 2 outcoming lines. So line and phase are the same. So in a delta, they're the same. In a Y, this is the phase delta, this is the phase current, and that's the phase current, and that's the line current. What I can see is I've got KCL where I have 2 currents that are going in opposite directions, so they subtract each other. So I line, if you did the vector math, is equal to the square root of 3 times I phase. That's for a delta. In the case of a Y, And these are connected this way. This again is the phase, but now my line is across those two terminals. I've got two power supplies and they have to be subtracted because it's VA minus VB. But then my phase current is the same as my line current. So that's how I have them set up. That's where the square root of 3. Again, it only comes from phasors. You notice it only comes from voltages and currents, nothing else. So just draw the picture and see what you can look at. And that should help you with the square root of 3. Anything else? TV land? It's always hard making these tests because if I get too real world, then it becomes a science project and nobody passes the test, right? Because then you spend your whole time trying to understand some of the jargon and terminology in industry. So you really have to write these a lot more, based on more simplistic stuff. But if you looked at the per unit homework and you looked at the transformer test, there's a lot of information in there. And so I'm trying to give you enough information you can see, hey, we need to bounce and use some of the jargon and terminology. So perhaps I can be able to do some of this stuff. All right, Mason, you want me to stop the video and then you can ask your question, or it would be helpful to stop it? Okay.
Hey, Paul, real
Yes.
quick, for those of us taking the test online, do you want us to print the test off and then scan it back in when we're
Yes.
done?
Yep. So you'll print the test, you'll do it on paper, whatever, and scratch paper. And then when you're done, you just scan it, either take, use your phone to take pictures and upload it that way. Or you can scan it. I prefer PDF because Brightspace, the grading works pretty well in PDF. Remember, I don't want to see a single submission with a MATLAB script. I don't want to see if you can write MATLAB scripts. I want to see if you understand the material. So I want to see your handwork, then show me the results, and then you can just use MATLAB as your calculator. All right. So MATLAB scripts are not adequate to show your work, just to be clear. If you want to write a MATLAB script, that's fine, but you don't submit it. That doesn't show me that you understand. I want to see the handwork done to do it. And if your handwork says see MATLAB script, you're not going to get any credit. Just to be clear. Does that answer your question, Scott?
Yes, thank you.
Sure. All right, anything else? I guess I will stop here, and somebody had one homework question, so I will handle this question, but after that, have a great day. See you all Monday in this room or on TV land. If you are going to take it remotely, make sure you have the lab link set up to log in. All right, take care, everyone.
Have a good one, Paul.
Thank you.